we would have different concentrations, such as if we would have here 1 molar of glucose on our left, and we will have 0.001 molar of glucose on the right. You see that's 10 to the third for the concentration ratio. We divide those two concentrations. So now I say, well, that takes me 3 packages of energy to achieve that concentration ratio. So if a molecule moves down, favored by this concentration difference, then we actually get a credit of 3 packages. Let's say that's negative 3 times 1.4 kilocalorie per mole. Now this was the example for glucose. Let's say that we have a charged molecule, an ion, like sodium. And that sodium can also be present at different concentrations. And that sodium, if it moves across the membrane in this direction, there will be a free energy change because of the concentration difference. And for this example, we can now see that the free energy change is the same as what we had for glucose a moment ago. It's going to be the negative 1.4 kilocalorie per mole. But since sodium is charged, and if there is a membrane potential, and if that potential is like so, then sodium is also favored to move in response to that membrane potential. So there's also a free energy change for that's possible. So that free energy change, once again, you don't have to remember, the delta G because of the membrane potential equals Z, the number of charges times the Faraday constant times the existing membrane potential given in volts. But we often give the membrane potential in millivolts. You have to think about that. So for the movement of sodium across a membrane, we have to consider the membrane potential, delta G volt component, and the concentration delta G component. So we add the two up. In this example that I'm drawing here, the movement of sodium is favored by both membrane potential and concentration. It could be the other way around. It almost never is in nature, but it could be, for the sake of argument, that the membrane potential is not favoring the movement of that sodium. Can you still see that? Yeah, you can still see that. We can still do all of our calculations. Now, the change in free energy that we get here for the movement of sodium, this is just an absolute value of that free energy. Whether this free energy change is going to be positive or negative is something we have to reason about. And in this case, because sodium moving from the left to the right, as indicated by my arrow, we see that as a favored reaction. We decide that ultimately the delta G in response to the membrane potential is going to be negative. If the membrane potential doesn't favor sodium movement, then that delta G is going to be positive. Now that's a special case where this example actually matters. And that's the case where we have, it's very realistic for animal cells, where we have a channel in a membrane and we have potassium concentrations. So we have potassium at 2 concentrations of a membrane. And let's just say we have 100 millimolar on one side and we have 10 millimolar on the other side. And we all know that potassium wants to flow down gradient, in this case to our right. We also know that as potassium moves through, there was of course chlorine or there were other negatively charged ions if this was a cell and there are negatively charged ions there as well. But as some of the positive ions move across, they leave the negative ions behind, creating a membrane potential that looks like this. I think you're all good with that. The question is, what is that membrane potential? The membrane potential that results will be the membrane potential that has a magnitude such that it completely eliminates the energy that is stored in the potassium gradient. So, potassium moves down gradient favored by concentration. But if the membrane potential builds up, there is a membrane potential at some point that counteracts that potassium movement. So the delta G due to concentration and due to membrane potential combined are 0. Delta G total is 0. That's actually the chemical definition of equilibrium. Equilibrium means potassium moves forward and backward just as fast. No net movement anymore. The magnitude of that membrane potential is given by, you should remember, the equilibrium potential, which at 27 degrees equals 60 millivolts times the log of, and we can just call it concentration 1 over concentration 2. And you can choose concentration 1 on the left or on the right, it doesn't matter. You get here with this equation, which is called the Nernst equation, you get the absolute value of the membrane potential that is established. We reason, in this case, that we will be positive on your right and negative on the left. And so we see that since the concentration 1 is 100 and 2 is 10, that ratio is 10, the log of 10 is 1, we get 60 millivolts. So now what we have seen is that 60 millivolts is also an amount of energy that can be equated to a 10 to the first concentration ratio. So a 10 to the first concentration ratio equals 60 millivolts. But we've also seen that this equals, in magnitude, 1.4 kilocalorie per mole. And we can call that one package of energy. And we can extend this and say, well, if we have a 10 to the second concentration ratio, that equals 120 millivolts equals 2.8 kilocalorie per mole, and that equals 2 packages on and on and on. And once you've arrived at that conclusion, you suddenly understand a lot of things. So let's play a game here. Let's imagine that we have a membrane. I'm going to surprise you a little bit with this one. We have a membrane, and let's just imagine that we have here 120 millivolts membrane potential. And let's just say it is like so. I'm going to ask you a question. If this was a real cell, will the left side be out, or will that represent the inside of the cell? If this is a plasma membrane, it's going to be the outside of the cell, which is something that we need to remember from the exam 1 material. So that this was out. Okay. Now let's say here we have sodium concentration of roughly 100 millimolar. And there we have a sodium ion concentration of roughly 10 millimolar. These concentrations are somewhat resembling the real concentrations for the insides and outsides of our cells. We have a little bit less inside and a little bit more outside in our case. Doesn't matter, we'll stick with this example. Now we have a transporter here, and we want to move glucose in. So So we want to move glucose, and let's say from a low concentration, let's just say from 1 millimolar up to 10 millimolar. I'm going to move it up. Can you still see the top? Good. Okay. Now, we can use the driving gradient of sodium to drive this. So sodium plus. Now my question here can be, this is not an exam question by the way, but just to make you understand it. How many sodium would you think are needed? Therefore, how many sodium have evolved to be co-transporter? So how did the co-transporter evolve? Did it take 2 sodium, 1, 2, 3, 0? You're saying 2. But this is, I said I'm going to surprise you. Okay, so sodium is going to move in. Sodium is favored by its concentration. 1 package, right? 1 energy package. -1, because I call it credit, and negative is credit in energy. Sodium movement is favored by the membrane potential also because we have 120 millivolts, and that's actually 2 standard packages that we get for the sodium. So we get 2, can you still see the top? 2 packages, negative there. So we have -3 sodium credits. So for the glucose, all we need to pay is we're going up from 1 to 10, so 10-fold concentration. For the glucose, we have to pay +1 package. So the net outcome of this is we have -3 we get for the sodium, +1 package for the glucose. We actually have -2 left. We have far more energy in the system to drive the glucose in. There's no need to take more than 1 sodium. There are transporters that take up glucose in cells using only 1 sodium. But that's not the way it works in the intestinal cell at the epithelium. This is the situation for any other cell in the body that takes its glucose from the bloodstream. Something like this. Not exactly, but something like this. However, if we have to go from a very low glucose concentration, like 0.001, then actually the quick math, I'll help you out there, this shows you this is 10 to the 4th of concentration to overcome. That is +4 packages to pay. Then the free negative credits that we get from the sodium will not work. So in that case, you need 2 sodium in the support mechanism. If you get that, that's nice. Another thing that's nice if you get it is for the synthesis of ATP, there's a certain amount of energy that is needed. That energy comes from protons. So we have an ATP synthase, it looks like this. It's the F1FO. It moves by allowing protons to go from typically a high to a low concentration, also favored by a membrane potential, which can be any value between 60 and 200. So as those protons move in this direction, it's possible for ADP and PI to react to form ATP, which is a steep uphill reaction. But there's a lot of energy stored in a proton when there's a significant concentration gradient and a membrane potential. And often the amount of energy stored per proton is between what I would call 3 and 4 standard packages. The amount of energy required to form ATP is roughly 8 to 9 of these packages, roughly 11 to 12 kilocalories per mole. So it takes a couple of protons in order to synthesize 1 ATP. 3 is the theoretical minimum. And so we see that these ion gradients are used for one of the most important processes in life. They're used to temporarily store energy. On the exam, there are roughly 5 occasions where you have to do anything that you can call a calculation. If you won't do that right, they might cost you 25 points. Maybe 30. I don't know. The rest is background, just knowing how glucose is broken down into various steps, how coenzymes are used in this process. I'm going to do an extra review for anyone who likes it. Just taking your questions tomorrow evening in Physiology 103 at 5. I will, when I'm back at my office, host, also when I'm available for questions of anybody who wants to come in before the exam on Friday. I think you're going to be fine.